Let us now take a closer look at the collapse of density fluctuations. The toy model that's often used is called the spherical top hat model. What it means is simply that there is a uniform overdense sphere embedded in a constant density background. As you recall from the last time, you can consider the background universe expanding according to the critical universe line. And then the fluctuation itself, which is overdense, acts like a little closed universe. So it splits from its background, and if it were a perfect model that can recollapse to a point, then it will be simply shown as the curve here. In reality, it does not collapse back in a point. It collapses to a certain finite radius in which system is in a virial equilibrium. But qualitatively, the density contrast, which is the difference between that line and the background line, grows as the universe expands. There is a turnover radius at the turnover time, and then there is a collapse that takes about the same amount of time as it took to get to the turnaround time, and the system ends up at some finite radius of the equilibrium state. Now, a simple argument to understand the final virial radius is that the system is just bound, so kinetic energy and potential energy are equal at the beginning. When it's in equilibrium state, a virial theorem state tells you that kinetic energy will be 1/2 of the potential one to within a sign. Now, if you look at simple formulas for binding energy of the self-gravitating system, you can see that potential energy is inversely proportional to the radius. And so if we're going to achieve a factor of 2 difference, that means that the radius of the final system will be 1/2 exactly of the initial one. And therefore, the density will increase by a cube of that, or a factor of 8. Now let's go back to the Friedmann equation. We can write it down as follows. And it has the well-familiar solution of universe expanding as a time to the 2/3 power. Now for the overdense perturbation, we can express the solution in a parametric form shown here. The derivation of this is beyond this class, but there are places where we can look it up, such as Barbara Ryden's book. For now, assume that this is indeed what's happening. So we can find out the turnaround time or radius by asking where is the maximum of this curve, which means that its first derivative is 0. Obviously, since this is a periodic solution, even though the universe would not necessarily bounce back, it tells us that for the first turnaround, it will be at the value of pi. And so the solution for this is given here. The turnaround time is given by this formula. Now, if we look at the background universe, which continues expanding, its density keeps going down. And the ratio of the densities of the sphere at the turnaround time and the surrounding universe is given as the cube of the expansion factors that correspond to them, which is a simple numerical factor of 9 pi squared divided by 16 for a very idealized case that we're talking about. But remember that by the time the universe collapses again to the virial equilibrium, its physical scale will go down by a factor of 2, and that means the density will go by another factor of 8. In the meantime, the background will get further diluted by a factor of 2 to the 3rd power to the cube, and that means 4. So there is an additional gain of a factor of 32 in density contrast. Multiplying these two together, the final virialized state of structure in equilibrium will be 180 times denser than the surrounding background. Remarkably, that's exactly what we see in large-scale structure today. This is the treatment of single idealized density fluctuation. Now, of course, what happens later, such density fluctuations, like dark matter halos, keep merging, building ever larger ones, and that is called a hierarchical formation scenario. Or also the bottom-up structure formation, because you build bigger ones starting from small ones. Now, in reality, the density fluctuations are unlikely to be perfect spheres. More likely, they can be approximated, say, as triaxial ellipsoids. They might have some very irregular shapes, but a triaxial ellipsoid is a better approximation than a sphere. Now, look what happens. At first, the perturbation expands within the surrounding universe. but then it turns around, and it will turn around first at its shortest axis, and it will start collapsing along the shortest axis while still expanding in the other two. So a three-dimensional blob will flatten itself into a pancake-like structure. And then it will turn around on the second shortest axis, and it will collapse along two axes and expanding on a third one. So the structure will turn into a filament. Finally, the third axis turns around, and what's really protocluster collapses along that axis, and it will become, again, quasi-spherical object in the end. This is the origin of the topology of the large-scale structure, that we see walls and filaments, and they intersect in things which really are clusters, and this is the simple reason why it happens. So let's figure out how long it will take for this to happen. Now let's divide initial density perturbation that's collapsing into a lot of thin layers. They will be all falling towards the middle. Let's say two adjacent ones are essentially subject to the same acceleration, the inner one slightly higher acceleration, so be falling in a little faster than the one just behind it. Therefore, the layers will never cross. The inner parts fall in fastest and the outer ones slowest. So if we take the point at the outermost shell and ask how long before that point collapses to the middle, that is basically the time for the collapse of the fluctuation, and it's called the free fall time. And since all of the mass is enclosed to that radius at all times, for all practical purposes, it is a free fall in the gravitational field of a point mass in the middle. And the solution for this is very simple, and it's shown here. You can also immediately see that intuitively, it is also true now formally that the lowest density fluctuations would collapse slowest and the highest density ones fastest. And also the largest ones would take longest time, the smaller ones would take less. Now if we plug in typical numbers, say for extent of dark halos of galaxies and sizes of clusters of galaxies, we find out that the relative collapse times are a few 100 million years for galaxies and a few billion years for clusters, which means that galaxies will collapse first in the early universe, and large-scale structures will be collapsing even today, and that's exactly what's observed. Next, we will talk about primordial density spectrum of fluctuations, which is a descriptor how many fluctuations of what size there are.